All right, so today we're going to talk about the one loop renormalization for scalars, and the way we will do it is by adding so-called counter terms, and we will also work in dimensional regularization, since, as I said, this is the most commonly used regularization. So first, let's understand a little bit the logic. So, as I said, we have infinities. We have infinities that we can regularize, but then we have to hide them somehow in the parameters of the theory. So, if we have a certain number of infinities, we hope to have the same number of parameters, and to basically say that something that is finite is equal to something that is infinite minus something else that is infinite. Basically, that is the basic idea, but we'll see that how it works in practice. So the particular example that we were going to use are one loop divergences for scalars. And as I said, phi to the fourth in d equal to 4 is the most relevant theory, one that is renormalizable in 4 dimensions. However, the one thing that it doesn't have with respect to the idea of renormalization is that for it we will have only the parameters coupling constant and mass, but it will not have, in principle, we could also redefine the field in itself, the field phi, but phi to the 4 does not have what is called wave function renormalization. Because of that, we'll also use the example of phi to the 3 in d equal to 6, which does have this wave function renormalization. Now, as I said, phi to the cubed is not technically a good theory, since the potential goes both to plus infinity but also to minus infinity, which means it doesn't have where to stop. It goes down all the way to infinity. But as a toy model for Feynman diagrams, we can think of it. And in d equal to 6, because again, this is the critical dimension, the dimension in which this theory is renormalizable, but not super renormalizable, as we said in the theory, in the lecture from Monday. So let's remember how that works. So let's remember first that we've derived the following formulas. We've derived that the dimension of the coupling lambda n of phi to the n was equal to d minus 2 n over 2, and the superficial degree of divergence of a diagram, omega of diagram D, was d minus 2 times e over 2 minus sum over the vertices of this lambda v. And as we also said, it's also more simple to consider the case where the dimension of lambda v is 0. Then we can ignore this, ignore the number of vertices. So first of all, let's check the dimension of lambda. So for phi 4, this would be 2. And then, as you can see, then we will get, wait a moment, what did I do? Yeah, it is right. So it is minus d plus 4. This is minus d plus 4. That means that the critical dimension is d equal to 4. On the other hand, if I have phi cubed, then I have 3 over 2 here. So then we will get 3 over 2 minus 3 over 2 d plus d is minus d over 2. And then plus 3. So again, we are correct that the critical dimension is d equal to 6. Now let's calculate these omegas. So then omega of d in the case 1 is d minus d minus 2 over 2e. That is 4 minus, here we get 1, 4 minus e. And in the case 2, we get 6 minus, here we get 2, so 2e. All right? Okay, so the other observation from last lecture was that we have what is called dimensional transmutation, which means that in the quantum theory, we have to introduce a dimensional object. We have to introduce something with dimension that is arbitrary, and the fact that it's arbitrary will lead later to the renormalization group. Now, in the case of dimensional regularization, as we've seen, if the dimension is not 4, it's 4 plus epsilon, then the dimension of lambda 4 is not 0. So in order to define some coupling that I'll call lambda tilde that is dimensionless, I have to multiply with something with dimension 1 to the power d minus 2 over 2, and this is in the general case, so let's say like this. All right.
So this new scale, so in other regularization, I can think of a physical interpretation of this new scale that introduced, but in this dimensional regularization, does this new scale have some interpretation?
No, that is the point of dimensional transmutation. There is no physical interpretation for it. It's truly an arbitrary scale, something that you know, it's not a mass, it's not anything, right? It's just a quantum scale, and the fact that it is arbitrary has physical implication. It will lead to an equation that, as I said, is called Kalman-Szymanczyk equation. All right? So it's truly an arbitrary scale that you have to introduce. All right. Right. So let's consider the first case of phi 4 in d equal to 4. All right? So we said that omega is 4 minus e. Right? So in order for, and as I said, this is a degree of, superficial degree of divergence. So the things that are divergent are the things with omega positive, which is e equal to 0, 1, 2, 3, 4. Also 4 is divergent because omega equal to 0 means log divergence, as we remember. All right, so, but on the other hand, another important point to remember, I said that we redefine parameters. But of course, when I mean that, I mean physical parameters, things that would appear, for instance, in the quantum effective action. So that means to say that we will only consider one pi Feynman diagrams. So e equal to 0 is out because that's just a vacuum bubble that doesn't appear in 1 pi. And then also we can check that in this particular theory, the one loop 1 pi for 1 and 3 it's actually 0. You can figure out by yourself that there's no way to write 1 pi diagrams at one loop for with one leg and 3 legs out. So that means that it's left only for gamma 2 and gamma 4. All right? And well, let's consider the dimension. Well, now I guess I'm changing the notation. I guess, I don't remember. Yeah, I think from now on. So in these formulas I used little d and capital D because capital D was for diagram. But from now on I will use capital D. And also dimension equal to 4 minus epsilon. And then if you look at this would be 1, and then n equal to 4, d equal to 4, that will give 0. And more precisely, since this is d equal to 4 minus epsilon, this will be multiplied by 2, so minus d plus d. So means that lambda tilde will be equal to mu to the epsilon lambda. All right. So for gamma 2, for the two-point function? Well, the only Feynman diagram that I can write is this one. There's nothing else to write that has one loop. It has to have one coupling and two legs. So then I would write that gamma 2 delta gamma 2 of P is equal to, well, lambda tilde minus lambda tilde over 2, because remember this has a symmetry factor of 2. I can switch these two lines, and then the integral of the one propagator. All right, and we have found the result for this integral in previous lecture, so we'll just copy it from last lecture. So this was m squared d over 2 minus 1 over 4 pi d over 2 gamma 1 minus d over 2. And then substituting also d equal to 4 minus epsilon, I get minus lambda m squared over 2 4 pi epsilon 4 pi squared, sorry, and then gamma epsilon over 2 minus 1 times 4 pi mu squared over m squared to the epsilon over 2. All right. So this is the first divergent object that we want, gamma 2. The next, gamma 4. So so if we talk about one loop and four legs, the only possibility is something like this, except I can do now some permutations. So let's say I define this P1, P2, P3, and P4. Right? So first of all, that's the only possibility because it's a one loop, and then at each point I have to have two external lines because I have 4-point interactions. But now I can do some permutations. I can write this diagram and this diagram. By which I have the same P1, P2, P3, P4, the same definitions. So in this one, you see that at this vertex, I have S equal P1 plus P4 squared. Remember, we have defined the Mandelstam variables. S is P1 plus P4 squared, which is also P2 plus P3 squared. And oh, sorry, what am I saying? No, this I mean that this is T. Sorry. Then S is P1 plus P2. This was P1 plus P2, which is also P3 plus P4 squared. And here we have this plus this, so that's P1 plus P3. So this is U is equal to P1 plus P3 squared, or P2 plus P4 squared. So the integral itself is the same because it's just one loop. It's an integral over one loop with two propagators. However, this one is something that depends on the external momenta via t. This one is something that depends on s. And this one is something that depends on u. And if I define I as just the integral, I can also remember that this is lambda tilde squared over 2. Again, this has symmetry factor s equal to 2 because I can switch these two lines. And the integral itself, let's say respect to t, and let's also define this object as P1 tilde. So P1 plus P4, define them as P1 tilde. Then the integral is just integral Q 2 pi d 1 over, so let's say that this is Q. Then here I have Q plus P1 tilde, so P1 plus P4. So this is Q squared plus M squared, Q plus P1 tilde squared plus M squared. All right? And also last lecture we have calculated a formula for the so-called Feynman parameterization of the general one-loop integral. And this is one with two points, which means it's one with two alpha integrals. So let's again copy the formula from last time and say that the result all this is sorry, let's say that I of t is equal to gamma 2 minus d over 2 over 4 pi d, integral from 0 to 1 d alpha 1 d alpha 2 delta 1 minus alpha 1 minus alpha 2. That was the constraint, that the sum of all the alphas is 1. And then we had this m squared plus alpha 1 p1 tilde squared plus minus alpha 1 squared p1 tilde squared to the power d over 2 minus 2. So let's write it in terms of epsilon. Actually, sorry. Yeah, I have to put lambda tilde squared over 2 because this also depended on the parameter epsilon, on the parameter epsilon through the dependence on mu. And here we have d is 4 minus epsilon, so here we get plus epsilon over 2 over 4 pi squared, and then also 4 pi epsilon over 2. Sorry about this, it's hard to write this nicely. I'm trying. Alright, so I have delta of 1 minus alpha 2. So let's do the integral over alpha 2 trivially, since alpha 2 does not appear, and then redefine alpha 1 as alpha. So this is m squared plus alpha. So and then here I have alpha minus alpha squared. So alpha 1 minus alpha p1 tilde squared. And the power in here is minus epsilon over 2. Alright, so this was one term, but I have also the other terms, the ones where I replace t with s, and the other one where I replace t with u. So, all in all,
excuse me, Professor, we are working in dimensions 4 minus epsilon, right?
yeah.
So the 4 pi in the denominator should be to the power minus epsilon over 2, right?
Right.
And there is a,
oh yeah, it is. Yeah, it is. It's just a typo. Sorry. Yeah.
and there is a extra 2 in the denominator also.
Sorry. Where it is? Here. Yeah.
There is an extra 2 in the denominator also, I think.
This one?
Yeah, one of
Yeah,
the
the
two.
one of simplified and then put it again and put the scale.
Yeah.
Okay.
You just substitute what is lambda to the right?
Oh, it's
It doesn't have this extra 2.
yeah. Yeah. All right. So let me keep it like this. All right, so then we get that delta gamma 4 of STU is lambda squared mu epsilon over 2 4 pi squared gamma over epsilon, gamma of epsilon over 2, the same 4 pi mu squared over n squared to epsilon over 2 times integral 0 to 1 d alpha, and now sum over, well, I equal to STU. Well, maybe not I, because I use I in a different context. Let's call it Z. Remember here, P1 tilde squared, this was what we call T. So here we have 1 plus Z alpha 1 minus alpha to the power minus epsilon over 2. All right, so these are the two divergent, the two divergences at one loop in phi 4. But let's extract more precisely the divergent parts. Meaning, let's expand this and find what's infinite and what's finite. So the one definition that I need is that one usually says that gamma of 1 plus epsilon is 1 plus epsilon psi of 1. So psi is actually, d gamma dz. Okay. All right. So with this definition, we have gammas everywhere. So let's start here. So we have gamma of minus 1 plus epsilon over 2. So that's, I have to relate to the origin one. So I have to wait a moment. Why did I say, well, yeah, I guess I just generalize it afterwards. Yeah, all right, so let's put it to minus 1, gamma of minus 1 plus epsilon. 1 appears here is minus 1 plus epsilon over 2, but we'll write that later. So gamma of minus 1 plus epsilon is gamma of epsilon divided by minus 1 plus epsilon, because gamma of something is gamma of something minus 1 divided by the same something minus 1. Multiplied by the same something minus 1. But now I want to remember to write this also in terms of divergent 1 over epsilon. So I have to relate again to gamma of 1 plus epsilon. So this is gamma of 1 plus epsilon divided by epsilon. So gamma of 1 plus epsilon is epsilon times gamma epsilon. And now I still had minus 1 plus epsilon. And now I remember that gamma 1 plus epsilon is, well, this is approximately, so to order epsilon is 1 plus epsilon psi of 1. So minus 1 minus epsilon. And then finally that I put this upstairs, so I get 1 over epsilon, sorry, minus 1 over epsilon times 1 plus epsilon 1 plus psi of 1, which is actually psi of 2. If you see, well, if you apply this one more, so anyway. So the point is we have the divergence minus 1 over epsilon, and then I have the 1 that gives the divergence plus epsilon times something. Now, so this is 1 over epsilon times epsilon, so this will be a finite part. So now we have to be careful when I do these kinds of expansions to separate the divergent parts and the finite parts. All right. So, delta gamma of 2 this one was minus lambda m squared over 2 4 pi squared. Oh, another observation is in both cases we found this 4 pi mu squared over m squared, both here and here, and this is a term that will appear often. So now one expansion was the one for this one that we just put in here, just that I replace epsilon with epsilon over 2. So I get minus 2 over epsilon plus epsilon over 2. 1 plus epsilon over 2 psi of 2. And then from this one, I get 1 plus epsilon over 2. So, you know, an object to an infinitesimal, I write it as e to sorry. E to the log. Sorry, what am I saying? Anyway, so the expansion of this is 1 plus epsilon over 2 log of 4 pi squared, 4 pi mu squared over m squared. And then this together is 1 plus epsilon over 2 psi over 2 plus log 4 pi mu squared over m squared. All right, so we note that we have calculated in this way both the divergent part, which is minus 2 over epsilon, and the finite part, in which 2 over epsilon and epsilon over 2 cancel, so minus this thing. All right? We will not need, in this lecture, the finite part, but we will need it later on, so it's a useful calculation. Similarly now, for gamma 4, we write lambda squared over 2 over lambda squared over 2 4 pi squared then gamma of epsilon over 2, as we said, is so gamma of epsilon is gamma of 1 plus epsilon over epsilon, which is 1 plus epsilon psi over 1 over epsilon. But now I have epsilon over 2 instead of epsilon, so this is 2 over epsilon, 1 plus epsilon over 2 psi of 1. And then the same expansion term here. So 1 plus epsilon over 2, epsilon over 2 log 4 pi mu squared over m squared. And now in the integral, what are we supposed to do? Well, fortunately, again, the power is infinitesimal, so I can just expand this as so expand this integrand as 1 plus minus epsilon over 2 log 1 plus alpha 1 minus alpha z. All right, and so for the divergent part, I just integrate this 1 over alpha, so that's just 1. But I have still sum over STU, so that's a factor of 3. So let's say it like this, 3 plus. But in the second term, I still have to do the integral. The second term, I have minus epsilon over 2. Sum over z is STU. Integral 0 to 1 d alpha log this 1 plus alpha 1 minus alpha z. Sorry. So.
Sorry, this you get expanding the integral. This last.
Sorry?
This last. I don't see.
So I expand the same thing. So something to an infinitesimal is 1 plus infinitesimal log of the something, right? So I wrote this, and then yeah. So the first integral was trivial, and now this integral is a bit non-trivial. It was with log. So this is kind of fortunate that I have only one integral, and it's of this term. Well, it's of this type, the alpha log 1 plus alpha 1 minus alpha, which actually turns out to be doable. In general, these kind of integrals of alphas are not doable, but I mean not doable in a complete form. But this integral this is minus 2 plus square root 1 plus 4m squared. Oh. Yeah, of course, yeah, this, I'm sorry, this was over m squared. I lost an m squared somewhere. Where did I lost it? Oh yeah, it was just here. Yeah, and everywhere else it should have been z over m squared. So m squared over z log square root 1 plus 4m squared over z plus 1 over square root 1 minus 4m squared over z minus, no, sorry, the same. So using this, you can actually calculate the log, the finite part as well. All right. Good. So, but let me finally write the divergent part. So this was lambda squared over 4 pi squared. Yeah, no, not m, yeah, epsilon. Yeah, that was taken care of. So 3 Oh no, yeah, sorry. So, yeah, let me just leave it like this. So there's a finite term that you can figure out by multiplying the epsilons, but for the moment I'm just interested in the divergent part, because this is also complicated. So if I would write the finite part, it will look very complicated. All right. So maybe let me write here gamma 2 is minus 2 over epsilon, and just erase the rest. All right. So let's do the same for 5 cubed in b equal to 6. So again, I have the tilde is to the epsilon lambda. But now I will define the d as 6 minus 2 epsilon. Just a redefinition. And now, as you remember, I said that omega was equal to 6 minus 2 epsilon. The superficial degree of divergence was omega is 6 minus 2e. So now again I have e equal to 0, 1, 2, and 3. Now not 4 anymore, but now it's just 0, 1, 2, 3. Since for e equal to 3, again I have omega equal to 0, which is a log divergence. So these are the ones that are superficially divergent. But again, e equal to 0 is a vacuum bubble, so it's not interesting. And then gamma 1, it's non-zero, but this actually just refers to a shift. In this case, you can check that it refers to just a shift into the value of phi. So it doesn't really redefine any parameter of the theory, and therefore we'll just ignore it. So the only gammas that are relevant are gamma 2 and gamma 3. Now, for gamma 2, at one loop, when one loop with 2 external lines, there's that. There's nothing else. You write one loop, you write 2 external lines, and that's it. So let me call this P, this Q, and then this is P plus Q. And again, symmetry factor of 2, because I can switch these 2 lines. So that gamma 2 of now depends of the external momentum P is lambda tilde 2 over 2. Again, integral over the loop momentum q, and two propagators, one with q squared and one with q plus p. All right, and again this integral we've calculated last lecture, so I just copy the result in here. And now I substitute this dimension as 6 minus 2 epsilon. So we get right. So I have to take m squared out of the integral, so we'll get an m squared multiplying here. So delta gamma 2 would be lambda squared m squared over 2. Then gamma of 2 minus d over 2. So that's gamma of the integer part is 2 minus 3, so minus 1. And then I have minus, so I have minus 2 here, divided by minus 2, so plus epsilon. Then I forgot, I suppose I forgot the 4 pi 3 that comes from this, and then I also have 4 pi minus epsilon. But more precisely, I can put this 4 pi upstairs, and then from lambda tilde squared, lambda tilde squared had the mu to the epsilon, so I have mu to the 2 epsilon. So mu squared as well. And I had also a factor of m squared. When I took it out of this result was, so this is 3 minus 2, 1. But then minus epsilon. So so I have m squared as well. So you see the same factor of 4 pi m squared over m squared appears as well. And then finally the integral. Now I divide by m squared, so it's 1 plus p squared over m squared, alpha 1 minus alpha, and the power was, as we said, 1 minus epsilon. Yeah, let me write also the way I did in my notes. Let me stop with the evaluation here. Let me write also the 3-point function. So, since we have phi-3 theory, at an external point I can only take out one point. So if I have a one-loop diagram, I can only construct one Feynman diagram for gamma 3. So again, gamma 3. Now let's call this P1 and this P2 and this P3, and then this Q1, this Q1 plus P1, then this is Q1 plus P2, or Q1 plus P3. That was the reasoning for writing P3 going out. So, so this one now is, now this one doesn't have any symmetries, so symmetry factor 1 minus lambda tilde 3 integral and now we have 3 propagators, so 1 over q1 squared plus m squared q plus p1 squared plus m squared and q plus p3 squared plus m squared. And again, we can use the general final parameterization, and I can write the final result. So minus lambda tilde cubed gamma 3 minus d over 2 over 4 pi d over 2 integral 0 to 1 d alpha 1 d alpha 2 d alpha 3 delta 1 minus alpha 1 minus alpha 2 minus alpha 3. But then we have m squared plus alpha 1 p1 squared plus alpha 3 p3 squared. Called it alpha 3 just because it multiplies p3. Then minus alpha 1 p1 minus alpha 3 p3 p3 3. Sorry, plus squared to d over 2 minus 2. All right. So now let's expand both of them into divergent and finite parts. So from this thing, gamma of minus 1 plus epsilon, I already expanded it. So delta gamma 2 is lambda squared n squared over 2 4 pi squared minus 1 over epsilon 1 plus epsilon psi of 2. That was, this part was gamma minus 1 plus epsilon. Then I still have this usual term, which is 1 plus epsilon, 1 plus, well, in this case, how did I write it before? 4 pi squared. Whatever. In my notes seem to have wrote it with minus, but it's 1 plus epsilon log 4 pi squared, 4 pi mu squared over n squared. And now the same as before, except that now we have this part to the power 1. So I have this 1 plus p squared over n squared alpha 1 minus alpha. But then as well I have 1 minus epsilon log of the same bracket. Right? So now for the divergent part, I still have to do an integral. I still have to do this integral, the alpha over 1 plus this, right? Which in fact, well, no, sorry, this is the one with log. So this one is actually easy to do now because the first term is so for this integral, the first term is 1, the second, and then I have p squared over n squared. Then I have integral of d alpha alpha, which is alpha squared over 1 over 2, so that's 1/2. But then I have minus alpha squared the alpha, so that's minus alpha cubed over 3, so minus 1 over 3. So this is 1 over 6, right? All right. So now the divergent part is calculated. You can write down you can actually calculate the divergent part if you're interested, but the final part if you're interested, but it's just expanding these things, these brackets that I wrote in here.
The divergent part depends on how you take the limit, right?
I'm sorry?
The divergent part depends on how you take the limit. instead of minus epsilon, now you wrote minus 2 epsilon. This is right or wrong? Just trying to. And the finite is independent. Is it right what I'm saying?
Again, you're jumping ahead. Yeah. So the divergent part depends on well, it depends how you separate the divergent part. However, as a function of the epsilon, I've defined d is 6 minus 2 epsilon here, and before I had d is 4 minus epsilon. Then there's no ambiguity as far as the epsilon dependence that I've written for this Feynman diagram. There's no ambiguity. I just calculated, right? I wrote a closed form and I expanded it in epsilon. There's nothing ambiguous in here. You're thinking about randomization schemes and all of that. Again, you're jumping ahead.
I wasn't thinking
anyway. So now I can let me just then.
Excuse me. Let me see if I understood your question. You were saying that perhaps if we define the dimension as 6 minus epsilon instead of 6 minus 2 epsilon, it will change anything.
the divergent part will change.
No, I just define this as epsilon tilde.
Yeah, if you did the calculation with epsilon tilde, then it will be.
But the final part will be the same, or it's like when you have a divergence.
The finite part is, of course.
So it's the same.
The final part is, yeah. So, yeah, I mean, the result is still the same. It's just you write it in terms of a different variable. That's the only thing that you're doing.
Yeah, it's obvious.
All right. So now the same thing for the same for delta gamma 3. The same for delta gamma 3, which was where did I write it? Here. All right, so this is minus lambda cubed. Minus lambda cubed. So this is this is 3 minus 3, that's 0, okay? And then the epsilon dependence is minus 2 over minus 2, so this epsilon. Right? Okay, so minus lambda 2, so then the expansion of that was 1 plus epsilon psi of 1 divided by epsilon, as we've seen before. Now this term is 4 pi to the power 3 minus epsilon. So 4 pi 3. And then m squared comes out with the same. So this term is now again 3 minus 2, 1 minus epsilon. Okay, so I take out m squared to the power 1 minus epsilon out of the integral. And this one is the lambda cube that I wrote. Then times mu to the 3 epsilon. Is that correct? Oh, something is amiss here. Well, anyway, yeah, I think I leave mu to the 2 epsilon, not epsilon, unchanged, and then I form the same combination that I formed everywhere. This one, 4 pi mu squared over m squared to the epsilon. Oh no, sorry, yeah, this is mu squared. I'm stupid. Yeah, so this is, I'm left with the mu to the epsilon. And here, no, here it was like this. And then I form the same expansion, and this I also expand as 1 plus epsilon log 4 pi mu squared over m squared. And then finally, I have to again expand the integrand in here. So integral Oh, stupid. There was a 3 in here. So there's actually, yeah, it's like this. The power is just minus epsilon. So yeah, but then there's no m squared in here. And m squared should have come from somewhere. Oh no, I didn't put m squared there. Sorry. Yeah. Sorry, I'm being stupid. All right. So I took up only m squared to the power minus epsilon, which just formed this combination, which I expanded again like this, and now, taking that out, I have integral of 1 plus something to the power minus epsilon. But again, for the divergent part, I just put this to 1. And then the integral of alpha 3 gives just 1. And then the other 2 gives also 1, because this is from 0 to 1. So the first term is just 1. First, the divergent term is just 1. But then in the expansion in epsilon, I will have now minus epsilon integral d alpha 1, d alpha 2. And again, I can do the delta function, because this depends only on alpha 1 and alpha 3. Sorry. I can do the alpha 2. And here I have log of that bracket. All right, so this is the final result for gamma 3 as well. So let me write down in a corner the divergent parts for phi cubed. So we've seen that for gamma 2, the divergent part was minus lambda squared m squared over 2 epsilon 4 pi squared. And that's it. And then delta gamma 3, and this phi 3 term was minus lambda cubed over 4 pi cubed no, minus lambda cubed over 4 pi cubed epsilon. Just that. All right, so this was the boring part, so to speak. Oh, wow. All right, so now let's understand the physics now. So, physics of counterterms. By the way, I wrote all of these calculations for you because eventually you will have to do one of these calculations, and you should be able to know how to organize these things. Otherwise, you will make some mistake, and well, it's useful. But now let's do some physics for this. Let's consider the idea of counterterms. All right, so we start, as I said, the idea of counterterms is that we have a number of divergences, and we're supposed to hide those infinities into the parameters of the theory. So the number of parameters that we have in your Lagrangian has to be equal to the number of divergences that you have obtained, order by order, in the loop expansion. Here we're doing just one loop. So in d equal to 4, we have found delta gamma 2 and delta gamma 4, and we had the parameters m and lambda. And so you can, yeah?
Excuse me, for the phi cubed theory in two-point function, shouldn't we have another term added to that? That is actually
Yeah. I think I probably forgot something. I am sure I forgot something. Where was it?
I think it's this times in a bracket.
Oh yeah. There was the integral. This one, right? Thank you. these terms. Yeah, I was actually wondering where that was, and I was going to hunt for it afterwards, but yeah, thanks. It was the integral over alpha that I forgot to put it in here. Good. So for d equal to 4, phi 4, we have two parameters and two infinities, and we hope to hide this infinity into this one and this infinity into this one, right? And so what we want to say is that we, in some sense, consider that the original parameters were infinite, and we've added something infinite to it, such that the thing that you actually measure is finite. Right? That's, roughly speaking, the idea. Now, first of all, let me digress a little bit and think about, so here I've given to you examples of renormalizable theorems, right? But what would happen if you would have a non-normalizable theory? Well, then, as I said last lecture, you would have, at each order, you would get a bunch of infinities, and eventually, you will have more infinities than parameters, so you have to invent parameters. That is to say, you add more kind of terms to the Lagrangian with some coefficient, and you try to hide the infinities in those parameters. So order by order, you can still deal with non-renormalizable theories, but it's a complete mess because at each order you have to do more renormalizing. All right, so the hiding of parameters, of infinities, amounts to adding what is called counter terms to the Lagrangian. So these are terms that are infinite and are supposed to cancel the divergence that we have found. So we add counter terms. So these are infinite, and you add it to the Lagrangian, and then cancel the divergence in loop. All right, so let's see specifically for this phi 4 what we add. This counter term field is something that, again, you have to hide the infinity into the parameter. So the term that I'm looking at is the quadratic term with the mass in front. So I have to put in here the divergence that, well, hopefully, did I write it? Actually, oh God, I had, well, never mind. So the divergence was lambda over 16 pi squared, 1 over epsilon. I thought I left it on the blackboard, but no, wait. This was it, but I was I was writing something wrong here. I was copying something wrong. No, this was it, but I was copying something wrong. This was supposed to be this. I'm not sure what I was copying. It was supposed to be lambda over 16 pi squared 1 over epsilon. Okay, and then the next term I will have to add is a phi-4 term to the, which was mu to the epsilon phi-4 over 4 factorial. Yeah. Again, I will separate this differently. So, yeah, here was also on mu to the epsilon, which I forgot. And then I have 3 lambda squared over 4 pi squared epsilon. All right, what do we think about this? Well, remember, if we think of this, so first of all, this one, the vertex that comes from this is minus the coefficient. So the vertex would be minus mu to the epsilon lambda squared over 16 pi squared 3 over epsilon. So this indeed, if you think of this as a new vertex to the theory, that you just add, so you think of this as this, the Feynman diagram, where this is the counter term, right? It's a vertex coming from this. This will just cancel this infinity. Now, you also think, well, okay, so m squared normally you think of it as a propagator, but think of it as a vertex. Then again, the corresponding thing would be minus the same thing. And this will cancel this divergence. So this would be a new divergent vertex, quote unquote. So it's a mass term, but think of it as a vertex if you want, coming from this counter term. This will cancel that divergence. Okay. Now, in principle, I could have also redefined d mu phi squared. So there's also a term in the Lagrangian d mu phi squared. And in principle, and since d mu is, well, it's d mu, it doesn't depend on anything. Phi, however, is a function, so in principle could absorb an infinity. So I could absorb this. This, as I said, would be called a wave function renormalization. But there was no such term, there was no such divergence in phi 4. So phi 4 does not have wave function renormalization. Right? The other observation that's related to what I thought you were talking about is that what I've added here, the counter terms, were only the 1 over epsilon terms. In principle, nothing stopped me to add something finite here as well. right? I could have added counter term which was 1 over epsilon plus something finite, right? This, so this term, this counter term that I had here is what I would call, what is called minimal subtraction. Since I just subtract the 1 over epsilon term from the divergent part. But in principle, I could subtract from these infinite functions. I could also subtract some minimal part, some finite part, excuse me, right? So this would be a different kind of subtraction. Now, well, we'll talk about in more detail about these kind of subtractions later on. So there's no need to dwell on it, but just to understand a little bit what happened. All right, so as I said, here it doesn't have wave function randomization, but that's why I gave the example of phi cubed, because it does have wave function randomization. So for phi cubed, the counter term is now, as Gabriel just noted, there's a term with p squared in here, right? So there's in the 2-point function, there's the m squared, and then the term where m squared cancels, and I'm left with just p squared. So I have this m squared plus p squared, which is you expect from a kinetic piece. So now the counter term part is just minus lambda squared 12 4 pi cubed 1 over epsilon times 1/2 d mu phi squared. Again, think of this as sorry. Yeah. Again, think of this as a vertex. If you think of this as a vertex, then the corresponding 2-point vertex coming from this counter term will be plus this thing, right? And this would cancel the part with p squared. And then correspondingly, then I would add minus lambda squared 2 4 pi squared 1 over epsilon 1/2 m squared phi squared. And this will cancel this divergence with m squared, again because the vertex, the counter term vertex is with plus this thing. This will cancel this with a minus from here. And finally, I have minus lambda cubed over 4 pi cubed 1 over epsilon mu epsilon phi cubed over 3 factorial. And again, the vertex is the vertex with the plus this bracket, which cancels the minus this thing. All right, good. So now let's organize a little bit the um, the theory of these counterterms. Just a moment. I seem to have lost something. No, it was like this. Yeah. Okay, so let's organize a little bit the theory of renormalization. All right, so in general now, so I gave you an example for a one loop renormalization. But in principle, you could do this to all orders. And then what happens then, let's say I have this 1/2 d mu phi squared plus 1/2 m squared phi squared plus mu to the epsilon lambda 3 factorial phi cubed. No, sorry, minus lambda. This minus lambda t. So this counter terms, then, as you saw, you just keep these kind of terms. Just keep these things, and you multiply it by some infinite value. So let's say c times 1/2 d mu phi squared plus b times 1/2 m squared phi squared plus a times mu to the epsilon lambda over 3 factorial phi cubed in this phi cubed theory, in which I have also wave function renormalization. All right, so we have the Lagrangian and the counterterm Lagrangian. And then we define the renormalized Lagrangian as the sum of the two. So this is something that depends on phi and lambda mu to the epsilon, right? It still depends on these things, but there is there's a finite coefficient here plus an infinite coefficient here. But now the logic is that phi m and lambda mu. So this Lagrangian is something that you use in your perturbation theory, right? In your Feynman diagram. But in it, the logic is that now these things are actually finite. They are the things that you actually observe, right? So usually this is stated in a different way. So, but the correct way, I think, is to say that numerically, the renormalized Lagrangian as a function of phi n lambda mu to the epsilon is equal to what is called the bare Lagrangian. In which I write just so in this thing. This thing looks like a classical Lagrangian, right? But the point is, in it, all the parameters are not, m0, lambda 0, and phi 0 are all infinite, right? So this bare Lagrangian, it's a kind of an abstraction in some sense, in the sense that it's written in terms of infinite objects. But the renormalized, so even though numerically these things are the same, conceptually they're different. This renormalized Lagrangian is written in terms of finite objects, things that you can actually measure, phi 0, m0, and lambda, right? But the coefficients in here are infinite. So that's why you have to do all of these Feynman diagrams.
Sorry, Professor, it seems something's missing for me, because in order to counter the infinity of the original Lagrangian, you put this counter there, but you treat this at 3 level to counter that.
That's right. That's part of what I was saying here.
Yeah,
right?
because you
So this bare Lagrangian, right? This is an abstraction, right? Because this is not really what you're supposed to be using to do normal Feynman diagrams. What you're supposed to be doing is the sum of Lagrange using this and this, where, as you noted, here I put one loop, and here I put the constant. But what happens? Why would I do this? Why would I add a term with, well, actually, yeah, I think I left it in here. Why would I add a term with one loop with a term with a 3 level? Well, because what you're doing is not 3 level or one loop or whatever. What you're doing is you're expanding in lambda. Lambda is your parameter, and as you here see, the counter terms have powers of lambda in them. All right. So what you're doing, I mean, that was the whole point. The whole point of the counter term was to cancel the divergent part of the one loop, right? So that's why I put a dependence on lambda in front of it. Okay. So what is missing then is that now. So now I write in general. So I write, let's say, phi 0 is square root 1 plus c, right? Just identifying this with this plus this, right? Phi 0, 1 plus phi. And similarly for the mass, and this is called actually Z phi square root, sorry. And then lambda 0 mu epsilon lambda 1 plus a Z phi n over 2. And then because of what we just said, these parameters lambda 0, m0 squared, and z phi, which are, remember, they are infinite, they also have a dependence on lambda that is non-trivial. So lambda 0, of course, starts with the usual, the measurable lambda. Well, there's epsilon as well. But then there's a function a1 of lambda divided by epsilon. And here there's m squared 1 plus b1 of lambda divided by epsilon. And here there's 1 plus c1 of lambda over epsilon, which is 1 plus c. This was all only at one loop. Now, if you go to higher loop, you generalize that instead of 1 over epsilon, in principle you find all powers of epsilon. So this generalizes to mu to the epsilon lambda plus sum over k equal to 1 to infinity ak of lambda over epsilon k, and so on, the other ones as well, the sum of bk over epsilon k and ck over epsilon k. Right? So the point was indeed that you can so as I said, this counterterm thing with a cross on it, this is a new vertex. So you can also do loops with them. I can do something like this, for instance, right? So but the only thing that matters is the dependence on lambda. That is what you're expanding at. So when you're calculating, we'll say it's a certain loop order. What you mean really is a certain order in lambda, which includes the original vertices and the counterterm vertices. Okay. So, well, I've given you some examples in here that you can figure out by yourself of what is A1, B1, and C1. You know, just extract from here what that was. I mean, there was something like this, you know, for phi 0, right? There was a dependence with lambda squared, and then with 1 over epsilon. So something like this was, so, yeah, so this was C1, yeah, this was C1, okay. Right, for instance. So you can do all these things. I have the example in here, but it's not important because we're already over time. But the last thing I want to tell you is that, to emphasize once again, I have emphasized this several times already, that quantum field theory, perturbation theory works as a tool. But you have to remember that is a very bizarre tool because you're expanding in lambda, which is small, but you have 1 over epsilon which is infinite. Moreover, you could have a small power of lambda, and then, as you see in here, I said epsilon power k, which is not infinite, but infinite to the kth order, right? So, so this perturbation theory is something really bizarre, and that's why mathematicians cannot understand how to define this properly. So, and physicists, I guess, just gave up or tried to do something else. But yeah, mathematically this doesn't make sense. But this is what you're doing. You're expanding in lambda, even though this is multiplied with something that is infinite. All right, that's everything I wanted to tell you today. Do you have more questions? Well, I guess you need to digest a little bit this renormalization, since this is the basis of quantum field theory. But yeah, maybe next time we can come up with more questions about it.
For its finite.
I'm sorry?
I hope that the time for its finite.
Yeah, okay. All right. So that's it. I'll see you on Monday, and please give me exercises